3 GHz is the highest frequency I was able to achieve with this Raspberry Pi 5. I wrote my own telemetry script, hacked the firmware and hooked up the Elmo Labs EVC2 to get the most out of my Raspberry Pi 5. In today's video, I show you how to overclock as well as undervolt the Raspberry Pi 5. I cover 3 distinct overclocking strategies. But before we get into the overclocking, let's first have a look at the hardware and the software that we'll be using in this guide. The Raspberry Pi 5 is a single board computer featuring a Broadcom BCM2712 SoC and an RP1 Southbridge chip for I/O connectivity. The BCM2712 is a 16nm SoC succeeding the BCM2711 of the Raspberry Pi 4. It is built around a quad-core ARM Cortex-A76. The core cluster has 512 KB per core L2 caches and a 2 MB shared L3 cache. Furthermore, the SoC also integrates an improved 12-core VideoCore 7 GPU. A 32-bit LPDDR4X memory interface provides up to 17 GB per second of memory bandwidth, while BY1 and BY4 PCIe Express interfaces support high-bandwidth external peripherals. Lastly, the SDIO provides a 100 MB per second connection for the SD card, which is the typical storage used for the Raspberry Pi. All these parts of the SoC are connected via a 128-bit data bus running at the VideoCore frequency. The system we're overclocking today consists of the following hardware. We use Ubuntu 23.10 64-bit and the following benchmark applications to measure performance and ensure system stability. In addition to benchmark software, we also need telemetry tools. Now, on Windows, I usually rely on hardware info because it provides me with a lot of system telemetry. But on Linux, it's a little bit more complicated to get that kind of information, especially for the Raspberry Pi. The most reliable telemetry is available through a command line tool provided by the SoC manufacturer, Broadcom, called VCGen Command. This tool communicates with the VideoCore IP block using the UART protocol. With the help of ChatGPT, Copilot, Gemini, and my brother, I put together a small Python script that gathers all relevant Raspberry Pi 5 telemetry, such as frequencies, voltages, and temperatures, and it outputs it both in the command line terminal and an easy-to-use CSV file. You can download the script from my GitHub page if you want to have a closer look. Before starting overclocking, we must check the system performance at the default settings. The default operating frequencies for the Raspberry Pi 5 are as follows. Here is the benchmark performance at stock. When running the S2E stability test, the average ARM clock is 2398 MHz with 0.896 volts. The average SoC temperature is 73 degrees Celsius. The average ARM core power consumption is 5.44 watts. Now it's time to increase the frequencies and hopefully also the performance. In our very first overclocking strategy, we will simply increase the frequency of the ARM cores and overvolt just a little bit. Overclocking the Raspberry Pi 5 is actually very easy. All you have to do is add a couple of lines to your config text file. Overclocking is done by setting the boot parameters in a config.txt file, which is located in the boot folder of the storage device. The easiest way is to simply add the lines to the config file. However, a fancier and cleaner way is to add your overclocking settings as a text file in the same folder and then include that text file with the config.txt. That's how I do it for my overclocking guide. I have a text file for each overclocking strategy and comment in or out the appropriate file depending on the settings I want to use. You can modify the files either directly from your Raspberry Pi 5 or by plugging the SD card into another computer. I'll show you how to modify these files at the end of this overclocking strategy. The Raspberry Pi 5 actually supports quite a bit of overclocking as it offers parameter adjustments for several clock domains. The 3 most relevant clock frequencies for this overclocking guide are the ARM, Core, and V3D. Unfortunately, unlike with the first Raspberry Pi versions, there's no way to set the memory frequency. The ARM core frequency was limited to 3 GHz when the Pi 5 launched in October 2023. However, following a GitHub issue from March 9th, Raspberry Pi firmware engineers unlocked the frequency in newer firmware versions. The VideoCore, ISP and HEVC clocks are linked together. The operating frequency will be the highest among the 3 configured domains. The V3D engine will run at the same frequency if you set the GPU frequency parameter. However, if you don't set GPU frequency or set the V3D frequency directly, it will operate at its own independent frequency. Configuring the frequency parameter sets the frequency upper bound of the voltage frequency curve. Likewise, frequency min sets the lower bound of the VF curve. You can force the frequency to the upper bound value by using the force turbo equals 1 parameter. Furthermore, you can also enforce the maximum turbo frequency from boot by setting the initial turbo equals 1 parameter. One of the more interesting aspects of overclocking the Raspberry Pi 5 is uncovering its dynamic voltage frequency technology, or DVF technology. This technology allows the Raspberry Pi 5 SoC to scale its frequency depending on its needs, and as the frequency increases, also the voltage increases. Each BCM2712 chip has a unique base voltage, Vpred, from the factory. This base voltage is added to a fixed DVF slope which increases with operating frequency. I think you can get the Vpred information by running the sudo vcgen command getconfig_int command. However, the value changes slightly every boot, and it's not entirely clear to me how it impacts the VF curve. Perhaps it's the predicted voltage required for the default maximum turbo frequency of 2400 MHz. Using our telemetry tool, we can map the ARM core's voltage frequency curve. We find that the minimum voltage is 720 mV for 1.5 GHz and below, then increases gradually to almost 887 mV at 2400 MHz. The 720 mV is a firmware-defined lower limit of the SoC voltage. Below 720 mV, the SRAM cache becomes unstable. This is a very common challenge with silicon chips. When we increase the upper limit of the ARM frequency to 2800 MHz without adding any voltage, we find that the voltage also increases to 944 mV. That's useful information because it means we can increase the frequency without worrying too much about the voltage. The Raspberry Pi 5 offers 2 ways to manually adjust the voltage. An option called overvoltage and another option called overvoltage delta. Overvoltage is the traditional method of setting the voltage, as it simply sets a fixed voltage. The overvoltage parameter ranges from -16 to +8, where +8 sets the voltage to 1 volt. I could only undervolt to -5, which sets the operating voltage to 760 mV. Overvoltage delta is a much more modern method of adjusting the voltage configuration, as it offsets the entire VF curve. Interestingly, the voltage offset can be both positive and negative, thus enabling undervolting opportunities for those looking to save more power. We find that there's also an upper limit to the voltage, 1 volt. This limit is enforced regardless of which overvoltage method is used. Open the Ubuntu terminal. Type sudo nano boot firmware config.txt and add the following lines. Include ocs1.txt. Write the file using Ctrl+O, then exit using Ctrl+X. Type sudo nano boot firmware ocs1.txt and add the following lines. ARM frequency equals 2900, overvoltage delta equals 25,000. Write the file using Ctrl+O, then exit the file using Ctrl+X. Then reboot the Pi. We rerun the benchmarks and check the performance increase compared to the default operation. Increasing the frequency by almost 21% increases the performance across the board. However, only in SysBench do we see linear performance scaling. The performance of the other benchmarks improves between 3% and 13%. When running the S2E stability test, the average ARM core clock is 2636 MHz with 0.98 volts. The average SoC temperature is 83.2 degrees Celsius.
The average ARM core power consumption is 7.58 watts.
From the stress test in our previous overclocking strategy, it's obvious that we're hitting a thermal limit. So in this overclocking strategy, not only will I increase the frequency of the video core, I also switch to a better cooling solution. Just like any other SoC on the market, the Broadcom BCM2712 has a thermal protection mechanism. The thermal throttling starts around 80 degrees Celsius, with the maximum allowed operating temperature being 85 degrees Celsius.
The initial throttling behavior is pretty benign as the frequency drops by only a few dozen megahertz. However, as we continue to operate at the thermal limit, the frequency throttling becomes more severe until eventually the ARM turbo boost is disabled and the frequency drops all the way to the base clock of 1500 MHz. While there's no way to override the maximum allowed temperature, we can further restrict it by using the temp limit parameter. The VideoCore frequency is tied to a variety of IP blocks on our SoC. Of these IP blocks, only the V3D engine can run at its independent frequency.
For this overclocking strategy, I'm primarily interested in increasing the frequency of the data bus that connects the ARM cluster of CPU cores with the video core and the memory subsystem. For this purpose, we can use the GPU frequency parameter. Still, I limit the V3D engine to its default frequency of 960 MHz. The GPU frequency, however, can be increased from 910 MHz to 1100 MHz.
Open the Ubuntu terminal. Type sudo nano boot firmware config.txt and add the following line. Include ocs2.txt. Write the file using Ctrl+O, then exit the file using Ctrl+X. Type sudo nano boot firmware ocs2.txt and add the following lines. ARM frequency equals 2900, GPU frequency equals 1100, V3D frequency equals 960, and overvoltage delta equals 25,000. Write the file using Ctrl+O, then exit the file using Ctrl+X, then reboot the Pi. We rerun the benchmarks and check the performance increase compared to the default operation. By increasing the VideoCore frequency from 910 to 1100 MHz, we see a further increase in the performance across all benchmark applications. When running the S2E stability test, the average ARM core clock is 2895 MHz with 1 volt. The average SoC temperature is 72.6 degrees Celsius. The average ARM core power consumption is 7.99 watts.
In our third overclocking strategy, we try to work around that voltage limitation. But that's easier said than done, because the voltage is actually handled in various places. Let's dig into the details.
As I mentioned earlier on, the Broadcom SoC has a dynamic voltage frequency technology that scales the operating frequency and voltage according to a predefined voltage frequency curve. In addition to the dynamic scaling, the VF curve also has an upper and lower limit for the operating voltage. In the case of the Raspberry Pi 5, the upper limit is 1 volt and the lower limit is 720 millivolt.
This behavior is actually very typical for any modern SoC. Any enthusiast who's overclocking AMD, Intel, or Nvidia chips will be very familiar with this kind of artificial limitation. Typically, these limitations can be enforced in multiple ways. Just like I do with any other SkatterBencher overclocking guide, let's have a look and see if we can work around this limitation. Let's start with the firmware. As I mentioned, we're all too familiar with this kind of an overvoltage artificial limitation governed by the firmware of the power management unit in the name of device security. And that's no different with the Raspberry Pi 5.
A Raspberry Pi community member by the name of Jonathan explains this very well in a blog post titled Beating Jeff's 3.14 GHz Raspberry Pi 5. To make a long story short, the first 3 boot stages of the Raspberry Pi include boot ROM, boot sys, and boot main. Boot ROM is the on-chip code that holds the secure keys. If secure mode is enabled, it will verify the signatures of the second state bootloaders, boot sys, and boot main. Bootsys verifies if the SPIE prompt signature matches the customer key in the OTP. If it does, then it will execute the boot main, which is also signed. The multiple levels of signatures effectively prevent us from simply modifying the Raspberry Pi 5 firmware and flashing custom firmware. This is similar how we can no longer flash our custom NVIDIA VGA BIOSes.
However, as a root Linux user on Raspberry Pi 5, we have full access to the system memory, including the memory that's used by the VideoCore IP block. Now, the VideoCore is actually responsible for booting up our Raspberry Pi 5. So, in theory at least, we could adjust the firmware at runtime. Since I've never done this kind of a workaround before, I was eager to learn how it works. Here's the process I followed.
First, I downloaded the firmware with the removed 3 GHz limitation. Then I pull apart the firmware using the RPI EEPROM tool's Python script. Next, we install the Ghidra disassembly tool. Ghidra will disassemble the binary code and piece together a higher level, more readable code. For that, we need a language file that will help with translation. While Ghidra does not have official support for the Broadcom VideoCore 7, fortunately, there's a VideoCore 4 architecture support file available, so we need to pull those into our Ghidra folder. Now we can open Ghidra, create a new project, import the boot main file, and select the VC4 language. Next, double-click the boot main file and let the software analyze the code. After the analysis is complete, we can search the program for any strings or code. In this case, we search for set-voltage and look for a function outside the global namespace. We find function 3FC 4C 6F2. This function appears to govern the voltage configuration. While it's not very easy to read, we can spot 2 variables, ivar1 and ivar2. If we follow the functions that define these 2 variables, we find that ivar1 returns 1000 and ivar2 returns 720. 720 of course stands for 720 millivolt and represents the minimum voltage of the SoC. 1000 is the 1 volt upper limit of the voltage.
The next step is to figure out how to change this value. As I mentioned before, the boot main is signed, so we can't just change this value in the boot main, put together a new firmware file and flash that on our Raspberry Pi 5. That's just not going to work. However, we can try changing it at runtime. And for this purpose, we memory map the system memory of the VideoCore on our device. We find the function that governs the upper voltage limit, and then we change that value at runtime. And then we hope our Raspberry Pi 5 doesn't go up in flames.
Again, with the help of Copilot, ChatGPT, and Gemini, I put together a Python script to do this. The script does 3 things. First, it verifies the voltage limit value at the target address to ensure that we adjust the right function. If the value matches, it updates that value to 480 in hex, which represents 1200 millivolt. Lastly, it flushes the VideoCore cache. The final thing to check is whether the modification actually worked. We can simply load up our Python telemetry script and run the stress test. We observe 2 key things. First, the measure volts arm command returns 1200, which matches our expectation. Second, the PMIC telemetry VDD core voltage output reached 1.099 volts.
What appears to happen is that we've successfully worked around the firmware voltage limitation, which means that the DVF technology can now request voltages higher than 1 volt. However, there's still a voltage limitation on the PMIC side. We'll dig into that in our next overclocking strategy. The final piece of the puzzle is to increase our clock frequencies. I further increased the ARM cores to 3 GHz, and I also overclocked the V3D engine to 1.2 GHz.
The additional voltage was too much for my small tower heatsink, so I added an additional fan to cool the heatsink. A quick shout out to Elmo Labs for providing the UPF and making it easy to use a standard computer fan.
A key issue with this overvoltage approach is that we set the voltage when we're in the operating system. However, the clock frequency is set at boot. So while the 3 GHz might be stable after we've increased the voltage to 1.1 volt, it's not stable when we're booting the Raspberry Pi.
Again, we turn to Jonatron's blog post for guidance. They explain we can create a service that configures a lower frequency as soon as possible during the boot process. Then, at runtime, we can increase the frequency after unlocking the voltage. Here's how you can create this service. First, you create a service to limit the CPU frequency. Then you add a file in the binary folder called slow CPU, and then you enable the system service. This will limit the frequency to 2500 MHz as early as possible. Open the Ubuntu terminal, type sudo nano boot firmware config.txt and add the following lines. Include ocs3.txt. Write the file using Ctrl+O, then exit the file using Ctrl+X. Type sudo nano boot firmware ocs3.txt and add the following lines. ARM frequency equals 3000, GPU frequency equals 1100, V3D frequency equals 1200, and overvoltage delta equals 25,000. Write the file using Ctrl+O, then exit the file using Ctrl+X. Then reboot the Pi. When you're back in the operating system, type sudo python3 vlimit override.py, type echo 3,000,000 sudo t sysdevices system CPU frequency scaling max frequency. We rerun the benchmarks and check the performance increase compared to the default operation. The performance uplift is noticeable across most benchmarks and peaks at plus 25.16% for Sysbench 1T. However, we also find our overclocked Pi is not stable for 2 benchmarks. We'll talk about that in the next segment. When running the S2E stability test, the average ARM core clock is 2995 MHz with 1.1 volts. The average SoC temperature is 59.8 degrees Celsius. The average ARM core power consumption is 11.03 watts.
In this segment, we further dig into the voltage limitation and chat a little bit about the remaining overclocking challenges. As you've seen from the previous overclocking strategy, even though we've worked around the firmware voltage limitation, there's still a 1.1 volt output limit on the PMIC side. So let's have a look at the PMIC.
The Renesas DA9091 is a general-purpose power management IC or PMIC suitable for the supply of complete systems in low-cost single-board computing applications. The input voltage is supplied directly from the USB at 5 volt. It integrates overvoltage, overtemperature, and overcurrent protections. It also features an I2C compatible interface. The PMIC integrates a high-performance multi-phase CPU buck converter, 7 single-phase buck converters, a current-limited power switch, 2 general-purpose LDOs, and a low-voltage LDO. Buck 8 provides the voltage output for our SLC. It's a 4-phase buck converter that supplies up to 15 amps continuous and 18 amps peak current. The output voltage is programmable between 0.5 and 1.1 volts.
The PMIC is software controlled using an I2C interface. Now, regular viewers of this channel will know that we very often rely on this I2C interface to work around certain overclocking limitations. And more often than not, we rely on the Elmo Labs EVC2.
The first challenge is to identify the relevant I2C pins, SDA for data and SCL for the clock. This was quite a challenge because those pins are not directly exposed on the PMIC. They are in fact hidden underneath the package. However, sometimes the I2C pins are also exposed on the PCB. So I called upon Elmore's expertise to search for the I2C pins.
So how do we identify these pins? Well, trial and error and 2 tools, our telemetry script and an oscilloscope.
Essentially, while the Raspberry Pi is running, we check each exposed pin for either a clock or a data signal. Since the telemetry Python script calls PMIC data, when the script is running, the database is much busier than when idle. After about 15 minutes of probing around, Elmore identified test points TP40 and TP41 on the back of the Raspberry Pi 5 PCB as the PMIC's SCL and SDA pins respectively.
Now that we have access to the PMIC I2C interface, let's explore. Unfortunately, the DA9091 I2C register information is not public information, And also the DA9091 datasheet is confidential, so unfortunately I will not be able to share the full document with you.
However, I can share the relevant PMIC registers for our purpose.
Let's start communicating with the PMIC using our Elmo Labs EVC2.
First things first, however, let's solder wires to TP40, TP1 and ground, and then connect those wires to an available header on the Elmo Labs EVC2 device. Now, let's open the EVC2 software. Here we browse to the header which connects to the Raspberry Pi 5 PMIC. We click on Find Devices and read the output message which says dev scan OK, found one addresses 38. That means the EVC2 found the device on address 38. Coincidentally, that's the default address referenced in the PMIC datasheet. Then, in the read-write segment, we switch to SMBus mode and use the following parameters to read out the buck8 vout information. This command returns 54 in hex, which translates to 84 in decimal. If we use the formula provided in the register description, we find that the voltage should be 720 millivolt. That's the expected voltage when the Raspberry Pi 5 sits idle. We can also try writing a value. However, keep in mind that the SoC still communicates with the PMIC, so any value we write will be overwritten by the dynamic voltage frequency algorithm. But we can try using the overvoltage parameter. So let's set overvoltage equals 8 and run the S2E stress test. If we now read the buck8 vout register, it returns 8C, which translates into 1 volt. Exactly what we expect based on this chip's VF curve. Now let's overwrite this value by using the following EVC2 command parameters. We can verify this value was written correctly by immediately clicking read. As a sanity check, we can also verify the settings with our telemetry script. We find that the measure volts ARM command returns 1000, which matches our expectation given the firmware voltage limit is 1 volt, and we find that the PMIC telemetry VideoCore voltage output reads approximately 1.09 volt.
Now that we know that the I2C communication works as expected, let's take the next step. In our case, we're trying to increase the vout of buck8, but we can already see a problem. The register is only defined up to 1.1 volt.
We can also write higher values to this register and read back our configured value. Unfortunately, while the register is programmed to a higher value, if we check the PMIC telemetry using our Python script, we find that the voltage output is still 1.1 volt.
The likely issue is that there's an undocumented and perhaps unprogrammable register that defines the maximum voltage output. Without this register, we won't be able to work around the 1.1 volt limitation using the I2C interface. As you've noticed from our previous overclocking strategy, even though our Raspberry Pi 5 is stable at 3 GHz during the S2E stress test tool, it fails 2 benchmarks, AI benchmark and passmark. And these 2 benchmarks have in common that they use the neon instructions.
If we have a closer look at the passmark benchmark, we find that the benchmark crashes specifically at the neon subtest. Furthermore, we find that it crashes also at lower frequencies even though it passes 2.9 GHz without the firmware voltage workaround. If we track the current voltage and power of the VDD core during the workload, we find that the neon subtest is significantly more power intensive than any other subtest.
When the benchmark crashes, the Raspberry Pi 5 completely shuts down. We have to manually press the power button to get it back up to working again. And also, during that shutdown period, we can't even communicate with the PMIC to see what's going on. The I2C bus is simply unavailable. That suggests that there's some kind of a protection kicking in. Maybe it's over current or over temperature protection. We don't know. Also, the debug registers of the PMIC are unavailable. So at the moment, it's hard to diagnose the root cause of this shutdown. Alright, let's wrap this up. I had the Raspberry Pi 5 on my overclocking to-do list for quite some time. I actually overclocked the very first Raspberry Pi many years ago, and that was a lot of fun. So I figured, why not have a look at the Raspberry Pi 5 and see if it's as fun. And it is fun, however, overclocking is severely more restricted. Not only was there this 3 GHz limitation in the very first launch firmware, overclocking is also limited for the memory. In fact, we can't overclock the memory at all. And in addition to that, there's also a voltage limitation, not just on the firmware side, but also on the PMIC side. That's not to say that I didn't have a lot of fun during this project. Actually, I learned a lot. I wrote my own telemetry script. I hacked through the firmware to find the voltage limitation, and also figuring out how to communicate with the PMIC using the I2C bus was quite the challenge. So all those things together made this project quite a lot of fun. And I still have some ideas on how to take this project to the next step, but that will be for a next video. For now, I want to thank you for watching and the patrons for their support. If you want to read through my guides, I will also put a written version of this guide on my blog. If you have any questions or comments, drop them in the comment section below, and see you next time.